Hello! In this lecture, we are going to start by introducing the perceptron, which is a linear classifier and a simple possible neural network composed by a single activation function. After having introduced the perceptron, we will make a step forward by introducing neural networks with multiple hidden layers and multiple neurons per layer. Let's start by looking at the structure of the perceptron. The perceptron is a supervised machine learning model used for binary classification. As you can see in the slide, the perceptron takes the input, which is assumed to be composed by m components. For instance, in the case of images, each of these components is the value of a pixel. Then the input goes through the linear combination with m weights, each of them is a scalar. The resulting linear combination is translated by adding a scalar, call it bias, denoted by W0 in the slide. The resulting linear combination plus the bias is passed through an activation function. As the perceptron is used for binary classification, this activation function is generally taken to be a step function, which is a nonlinear function that maps its input to a class 0 or 1. In what follows, we will often simplify the notation and represent perceptrons with a simplified notation where we only represent input neurons, connection, and activation functions. Let us now try to make a step forward and move from perceptron to neural network with one hidden layer. A neural network with a single hidden layer, also called shallow neural network, generalized perceptron with multiple activation functions, k in the example of the slide, and multiple outputs. Specifically, different linear combinations of the inputs are passed through k activation functions. A linear combination of the output of the activation functions then defines the output of the neural network. This can be written in vector form, where W0 is the matrix of the weights of the first layer, the one connecting the input to the activation function, and B0 is the vector of biases of dimension equal to the number of activation functions. Note that in this notation, A is a vector of length k. This means that sigma represents a vector of k activation functions, one for each neuron in the hidden layer. If instead of one hidden layer you have more hidden layers, then the mathematical definition follows trivially from the one hidden layer case, by simply connecting hidden layers to other hidden layers. If you look at the two hidden layer neural network in the figure, you can see that in the first two layers, all inputs are connected to all activation functions. A layer with such property is called dense. In contrast, the output layer is not dense because, for instance, the first hidden neuron is not connected with the end output. If all layers of a neural network are dense, then the neural network is called fully connected. Fully connected neural networks are very general and flexible models, which are widely applicable and with success in many applications. However, their performance is not often as good as specialized structures built for a specific problem. For instance, in the case of images, their performance is generally not as good as that of convolutional neural network. Convolutional neural networks, in particular, are built under the specific assumptions that inputs are images, and the neuron connections are built to take advantage of the geometric properties that can be inferred from pixels. As discussed, one of the key components of neural networks is the activation function. The role of the activation function is to introduce nonlinearities in the network. Historically, the activation function employed for neural networks was the sigmoid. The sigmoid is a function that is monotonically increasing and bounded between 0 and 1, and resembles a step functions but has non-zero derivatives. During the years, the sigmoid has been shown to be outperformed by the hyperbolic tangent, which has the advantage to map negative values to a negative output. Consequently, it can distinguish from negative and close to zero inputs. In practice, training with hyperbolic tangent activation function with the hyperbolic tangent is generally simpler compared to sigmoid. However, both hyperbolic tangent and sigmoid have the gradient vanishing problem. That is, for some input regions, the gradient is extremely small. This makes training via algorithms such as gradient descent inefficient. As a consequence, both the sigmoid and hyperbolic tangent functions are not widely used nowadays. The most common activation function is the ReLU or rectified linear unit, which is given by a linear function saturated at 0. Note that, unlike the perceptron case, we did not consider a step function as activation functions. This is because for the step function, the gradient is 0 everywhere except at 0 where it's not defined. This makes not a good choice if you train neural networks with gradient descent based algorithm. Note also that ReLU is not differentiable at 0. However, in practice this is often not a problem, because in any neighborhood of 0, the function has gradients to a constant value, 1 or 0.